So up until this point, we've been able to find the probability of any event or outcome given an experiment. But now we want to look at the bigger picture and to be able to look at the experiment itself as a whole, and to be able to study this experiment and draw some conclusions. And in order to do that, we need to study all the possible outcomes of an experiment. So to help with this, we define the concept of a random variable. So a random variable is very similar to what you see in math, which is just a normal variable. It's going to take the form of a letter, usually capital X, and it's defined as being any possible value / outcome in an experiment. So if my experiment was rolling a 6-sided die, so let's say my experiment was rolling a 6-sided die, then my corresponding random variable, you'd define it like this. We'd say let x be the number that the dice lands on. And it's very important that you define your random variable because it's just a letter, so without this definition, nobody's going to know what you're talking about. So given our experiment where we're rolling a 6-sided die, we let x be the number that the dice lands on. So all the possible outcomes for our experiment, x can either be 1, 2, 3, 4, 5, 6. So these are the possible values that our random variable can take. Now before we move further, we need to talk about the types of random variables. So there's two main primary types that a random variable can be. This is a qualitative random variable, and these are your random variables that are non-numerical. So for example, if I chose a random person on the street and I asked him which age group he fell in, so let's say from 0 to 10, 11 to 20, and 21 to 30. And then we have 31 and above. So these are age groups. Or you could look at them as being categories. And the main point here is these are not numbers. They consist of numbers, but the structure here is a group. So since they're groups, they are non-numerical. So that's one type of random variable. The second type of random variable is a quantitative random variables, and these are numerical. So just like how we have x over here as being the number that the dice lands on, 1, 2, 3, those are numerical quantities. Now for the purpose of this course, or mainly for the study of probability, we're going to disregard qualitative random variables and we're going to focus on numerical values. Now within these numerical values, we have two subcategories. So we have discrete random variables and we have continuous random variables. So this first category, which is discrete, these are values that are finite in nature. Or you could look at them as being limited, or having gaps in between. So if we look back to our experiment where we roll a 6-sided die, x could be 1, 2, 3, 4, 5, or 6. It couldn't be more than 6. It also couldn't be less than 1. But most importantly, if I chose a number in between any two outcomes, so if I chose 1 and 2, if I wanted to find a number in between 1 and 2, so let's say 1.5, this is not a possible outcome. And so in between each possible outcome, we have a gap of 1. So this is a discrete random variable. In contrast, you have the idea of a continuous random variable. And the wording here is really important. It's continuous. So there's no gaps in between outcomes. And there's infinitely many outcomes. So for example, let's say my experiment, or I define a second experiment, where I go out and I select a random person and I measure their height in meters. So now x is the height of the person in meters. So let's say the first person I find, he's 150 meters tall. A second person I find is 151 meters tall. This data set is continuous because my random variable can take on any possible value. So if I want to find a value between 150 and 151, I can find infinitely many. So I could find 150.0001 meters. I could also find 150.001 meters, and I can add infinitely many zeros, and those are all valid values. I could also find a person that's 150.5 meters, another person that's 150.75 meters, and every time I can choose the midpoint between my two closest values and I can find another value. So in most cases, if your value can have decimals, it's going to be continuous. If there's infinitely many values and you don't have gaps in between them, it's very important that you don't have gaps in between values. If I can always find a value, a possible value between any two adjacent values, then my variable is continuous. So some examples of continuous variables would be time. So maybe I'm looking at the time that someone finishes a race. One person could finish in 10 seconds, another person could finish in 11 seconds, and I could have another person finish in 10.5 seconds or 10.01 seconds. And there's infinitely many values in between 10 seconds and 11 seconds that I could take. So time is an example. We just saw earlier that height was an example. We also have money as an example, and you could go on. So the whole point of defining a random variable is so that I can create a graph where my x-axis is the possible outcomes, or x, and my y-axis is the corresponding probability for this outcome. When I graph these pairs, I'm going to get some shape. If it's a continuous variable, I will get a continuous function. If it's a discrete variable, then I will have gaps in between my possible values, and usually you show that as a bar graph. And these graphs, of course, are called probability distributions because they show you how the probability changes or is distributed along all the possible outcomes. Now to make this more clear, we'll go back to our example. So let's say my experiment, once again, is rolling a 6-sided die. And we let x be the number we land on. Then the possible values for this variable x are 1, 2, 3, 4, 5, and 6. And we already know that every single side on a dice is equally likely to be landed on. And so p of x, when x is equal to 1, so p of 1 over here, that's equal to 1 out of 6. The same thing is true for 2, it's 1 out of 6. For 3, it's 1 out of 6. For 4, it's 1 out of 6. For 5, it's 1 out of 6. And for 6, it's 1 out of 6. So when I graph this, it's a discrete variable, remember, because each adjacent value has a gap of 1 in between. I can't roll a 1.5. I can only roll a 1, a 2, or a 3, and so on. So when I graph this, I'll draw a bar graph all the way to 6, and on my y-axis, all my probabilities are going to have heights of 1 over 6. All the way to 6. So if you wanted to look at it in a different way, maybe I can have any possible integer value, but in that case p of 0 would be 0. P of anything greater than 6 would also be 0, and anything less than 1 would be 0. And if I look at my graph here, I can see that all the probabilities are equal. So that's why I have a flat line at the top. And this distribution has a special name, which we'll see in a couple seconds. So in the case where all events or all outcomes are equally likely, which another word we can use is equiprobable, in that case, your resulting distribution is going to be a uniform distribution. It's called uniform because every single probability for every single outcome is the same, or uniformly distributed. So when we graph this kind of experiments, you'll have some probability up here, and every single outcome is going to have the same probability, so you end up with a flat line. And the form of this distribution is a p of x. So this is p of x, this is x. P of x is equal to 1 over k, where k is the number of possible outcomes. K is the number of possible outcomes. So in the example of rolling a 6-sided die, we had 6 possible outcomes, 1 through 6. So in that case, k was equal to 6, and we knew by intuition that every single side is equally likely to be landed on. So p of x for each one of these sides is equal to 1 over k, which is equal to 1 over 6. So my graph for rolling a 6-sided die, where this is x, my probability is 1 over 6. Every single value from 1 to 6 has a probability of 1 over 6. After that, the rest of my probabilities are equal to 0. So we could say p of x is equal to 0 otherwise. So if we had p of anything less than 1, so p of 0, that's equal to 0. P of anything greater than 6, so p of 7, that's equal to 0, and so on. Now the fact that the probabilities over here are constant makes this distribution very uninteresting, and you won't really see it much, but it's a nice introduction for the concept of probability distributions. Now, a much more interesting distribution to study is the binomial distribution. So in this case, we have an experiment which consists of successive trials. And a trial is simply a repetition of the experiment. Each of these trials has 2 outcomes. Either a success or a failure. So you're going to define what a success is and a failure is based on the question that you get, and this will become more clear as we do an example in a few moments. Before we get to that, our success is going to have a probability of p. So p is going to be some number between 0 and 1, and that's the probability of having a successful trial. The probability then of a failure, since we have two outcomes, the probability of all the outcomes has to add up to 1. Then the probability of a failure, we're going to call it q, but q is going to equal 1 minus p. So whatever p is, 1 minus p, that's going to be the probability of a failure. So we have these two outcomes. It's very important to have a binomial distribution that these two probabilities, probability of success and failure for each trial, remains constant. So these probabilities cannot change between trials. And for our binomial distribution, we always define x as being the number of successes in some amount of trials. So in this case, we'll say n trials. So the example we'll see is we're flipping a coin 3 times. So in this case, you have 3 trials. So n is equal to 3. And we're going to ask the question, how likely, or what is the probability, how likely is it to get, or to flip 2 heads? Out of these 3 trials, how likely is it that I get 2 heads? So my success in this case, since I'm looking at the probability of getting 2 heads, my success is going to be flipping heads. My failure is going to be flipping tails. And the corresponding probabilities, p is going to equal 1/2, and q, which is equal to 1 minus p, 1 minus 1/2 is also 1/2. And the formula for this distribution, which we'll explain as we do the example, but I'll just give you the formula for now, is p of x equals k. So k is the number of successes. So in this case, k is equal to 2, since we want to flip 2 heads out of these 3 trials. So p of x is equal to k. That probability is how many ever trials you have, so n, choose k, so I'll write it in a more familiar format, n, choose k, multiplied by p to the power of k multiplied by q to the power of n minus k. And we'll see where this comes from as we do the example on the next page. Alright, so an experiment consists of flipping a coin 3 times. What is the probability of getting 2 heads? That's the example we just saw. So we're flipping a coin 3 times. Our number of trials, or n, is equal to 3. We're asking the question, what is the probability of getting 2 heads? So we're specifically focusing on the landing of heads. So our success, in this case, is landing heads. Our failure is landing tails. And we're looking at getting 2 landing of heads. So that's 2 successes, which is equal to k. The probability of success, or landing heads, is equal to 1/2. The probability of failure is equal also to 1/2, or 1 minus 1/2 is equal to 1/2. So our formula was p of x is equal to k is equal to n choose k, p to the power of k, q to the n minus k. So let's see where this comes from. We have 3 trials, so 3 possible spots. And we want to know the probability of getting 2 heads. So the first step over here is how many ways to choose 2 spots of 3 as getting heads, or as getting a success. So we have 3 spots and we need only 2 heads. So we need to choose 2 of these spots as being heads. That's the same question as saying 3 choose 2, which is equal to 3. So there's 3 ways in which we can get 2 heads. And if you actually write them down, you can see that you can get 2 heads back to back and then a tails. That's 1. You can get a heads followed by a tails followed by another heads. That's 2. And you can get a tails first followed by back-to-back heads. So that's 3 possible ways. There's 3 ways that we can get 2 successes out of 3 attempts. So that's step 1. That's why we have this n choose k over here. That's just how many ways you can choose k successes out of n trials. So now for each one of these possible ways, what is the probability? What is the probability of each of these events? So we have 3 events where we get 2 heads. What is the probability of each of these events? So in all cases, we have 2 heads and 1 tails. So these are successive events. So all you have to do to find the probability is multiply these individual probabilities. So the first case, what is the probability of landing heads? It's 1/2. What is the probability of landing another heads? It's also 1/2. So these are our 2 successes over here. And then what's the probability of getting a failure? It's also 1/2. So in each case we have 2 successes. So I'll write these in a different color to make this more clear. The probabilities of our successes is 1/2 multiplied by 1/2. The probability of our failure is also 1/2. It's the same for all of our trials because we get 2 heads in each one. So we multiply the success twice. That's why we have p to the power of k. The probability of success to the power of how many times that success occurs, because it's the same thing as saying 1/2 to the power of 2. Then we multiply our failures by the remaining spots in our experiment. So we have 3 trials, 2 successes, so we have 1 failure left, or 3 minus 2. That's why you have n minus k up here. And in this case, that's this 1/2 over here, because in each experiment we need to get 1 tails in order to only get 2 heads. So in the end, the probability of getting 2 heads, prob 2 heads, is the same thing as p of x is equal to 2, which is choosing 2 spots out of 3 to be our successes. Then we have our successes, we have 2 of them, so 1/2 to the power of 2. Then our failures, we simply multiply by 1/2. So that's equal to 3 times 1/2 to the power of 3. And we got lucky in this case because the probability of a success and a failure is the same. In the next example, it won't be. This is equal to 3/8. And if you simply wrote down all the possibilities, you'll see that there's 8 possible total outcomes when you're flipping a coin 3 times. 3 of those possible outcomes have heads twice, and so this checks out. So our next question has an archer that's able to hit the bullseye 70% of the time, and he needs to hit at least 4 bullseyes in 5 shots to qualify the Olympics, and we want to see how good his chances are. So in this case, we're focusing on the event where he hits the bullseye. So our success in this case is hitting the bullseye and that has a probability P equal to 0.7 or 70%. That means our failure is missing the bullseye, and if he hits it 70% of the time, then that means he misses 1 minus 0.7 equals 0.3 or 30% of the time. He has a total of 5 shots, so n is equal to 5. We have 5 trials, and he needs to hit at least 4 bullseyes. Now the important thing to notice here is the question says at least. So k is equal to 4 or 5. Another way to word this, or to write it, would be p of x. First we need to define x, so in this case, let x be number of bullseyes hit. So another way to word this would be the probability of x being greater than or equal to 4, which is the same thing as saying it is at least 4. And that's equal, since this is an OR case, the probability of getting 4 bullseyes plus the probability of getting 5 bullseyes, which is equal to, we have 5 spots, 5 trials. We want to choose 4 of them to be successes. That means that we have a success 4 times, so 0.7 to the power of 4, multiplied, one of the spots needs to be a failure, so 0.3. To the power of 1, 5 minus 4, that's equal to 1, so we'll just keep it as 0.3. Then we add the probability of getting 5 bullseyes. So we have 5 spots, all 5 of them need to be bullseyes or successes, and that means we only have successes, so 0.7 to the power of 5, and 0.3, we have no failures, and you can see that 5 minus 5 is 0, so this simply reduces to 1, so we have no failures. If we work this out, there's 5 ways that you can choose 4 spots to be successes out of 5 trials. 0.7 to the power of 4, 0.7 to the power of 4 is 0.2401 times 0.3 plus, there's only one way to choose 5 spots to be successes out of a total of 5 spots, and that's the case where every single spot is a success, so that's going to be 1, and 0.7 to the power of 5 is 0.16807. When you add these together, you'll get a final answer of around 0.522822. So in that case, we can have a final statement. How good are his chances? He is around 52.8% likely to qualify. And that's your answer.